In this next section, we're going to take a look at the details of the regulation of blood volume by the kidneys. We will revisit this in more detail again when we cover renal physiology in chapter 17. But urine begins with something that's referred to as filtration. That is, there's a capillary bed in the kidneys in a structure that's called glomeruli, where liquid leaves the capillaries and enters into the tubules of the kidney. Because it goes through a variety of different pores on its way from the capillaries into these tubules, it's referred to as filtrate because it gets filtered as it leaves the capillaries and enters into the kidneys. So this liquid is initially referred to as filtrate. As it goes through all the tubules of the kidneys, it gets modified in a very significant number of ways, and then at the very end, it becomes urine. But before that, it's still referred to as filtrate. We make an absolutely mind-numbing amount of this, 180 liters a day. We only have 5 liters of blood. So this is a phenomenal amount of filtrate. So almost all of this liquid has to get back into the blood almost immediately or we would dehydrate to death. We make only about 1.5 liters of urine per day. So 99% or more of this filtrate then is reabsorbed back into the blood. And again, we're going to use these terms again over and over, so let me define these for you again. But absorption is the movement of the substances that we eat, liquids and foods that we eat from the intestines into the bloodstream. That's absorption. Reabsorption is recollecting that. Some of that stuff can end up in the filtrate and could end up in the urine, but large amounts of this, things like glucose, amino acids, are reabsorbed back into the bloodstream. So how much of this is reabsorbed is controlled by several hormones. We will discuss these in a moment, and also by the sympathetic nervous system that's going to regulate blood flow, for example, to the kidneys. And this is all to try to keep blood volume and blood osmolality in a normal range. So let's take a look at the sympathetic nervous system. So this works in part because if there's an increase in blood volume and an increase, as a consequence, an increase in venous return, this stretches the atria. They have stretch receptors in the atria that then impact the degree of activation of the sympathetic nervous system. So this increases heart rate and help to move that extra volume of blood along, but it also decreases the stimulation to the kidney. What happens is the decrease of the stimulation to the kidney causes the arterioles in the kidneys to dilate as a consequence of that. This increases blood flow to the kidney. That increases then the rate of filtration, which then increases the amount of urine that's produced, and as a consequence is going to drop blood volume. Now, another aspect, another hormonal aspect of this is antidiuretic hormone that we've discussed over and over again and will continue to revisit. And if you remember, this is produced by the hypothalamus and released by the posterior pituitary, and it's sensing receptors are sensing the osmolality of blood plasma. Well, in fact, actually, it works another way as well. That is, if there's a drop in blood volume, they're activated as well. So excessive osmolality can happen because either you're eating too much salt, salty bags of potato chips, for example, or you're getting dehydrated and not drinking fluids. You're running a 10K or playing basketball or something, but you're not drinking fluid, will cause a drop in blood volume and an increase in blood osmolality. In addition, the increase in plasma osmolality then affects centers in the hypothalamus that trigger the sensation of being thirsty, so it provides motivation for drinking fluid. Antidiuretic hormone, we'll get into much more of the details of this in the kidney section, but it stimulates water reabsorption by inserting aquaporins in the collecting duct of the kidney. This allows water to leave what could become urine and be reabsorbed back into the blood. It's going to dilute the blood, bring the osmolality down, and bring blood volume back up. Okay, so let's take a look at that some more here. So increased water intake, because you're being thirsty, and decreased urine volume is going to increase that blood volume. The blood becomes more dilute because of antidiuretic hormones' effect on aquaporins is bring water back into the blood, and that's going to dilute the blood. And once the blood becomes dilute back down to normal, antidiuretic hormone concentrations are dropped as a consequence of that. There are also stretch receptors in the left atrium and in the carotid sinus. This is part of the carotid arteries, and in the aortic arch, part of our blood vessels that are leaving the heart, that also inhibit the release of antidiuretic hormone. Again, it's sensing that there is a large blood volume, and a way to drop that is to remove antidiuretic hormone and have more of that filtrate become urine, and as a consequence, reduce blood volume. Stretch receptors in the atria also stimulate the release of something called atrial natriuretic peptide. And what this is going to do is cause salt to be retained in the filtrate and the excretion of additional salt in the filtrate. This is going to bring water with it. And so it's going to increase urine volume and decrease blood volume. So here's a table here, a chart showing how this works. So you get dehydration from one reason or another. Again, you're running a 10K and not drinking, or salt ingestion, potato chips or whatever it is that you're eating that is excessively salty. This is going to bring your blood osmolality up. Osmoreceptors in the hypothalamus then are going to trigger the posterior pituitary to release antidiuretic hormone. Antidiuretic hormone then is going to insert aquaporins in the collecting duct in the kidney. These aquaporins are going to allow water to leave the kidneys and be reabsorbed back into the bloodstream. So this is going to increase blood volume and drop blood osmolality. Likewise, the osmoreceptors in the hypothalamus evoke this sensation of feeling thirsty. And so this is going to make you drink more fluids, which is going to increase your blood volume and drop your blood osmolality as well. So then let's take a look at aldosterone. This is another hormone that influences blood volume. So this is secreted, if you recall, by the adrenal cortex. And I say indirectly because you'll see down here there's a whole system of events that have to happen for aldosterone to get released. And so aldosterone is released when blood pressure and blood volume are reduced, indicating that volume then needs to be increased. And so what aldosterone does is it works basically the opposite of atrial natriuretic peptide. We'll come back to that in a moment. But it causes the reabsorption of salt, and that brings water along with it. It doesn't change the blood osmolality, because when the salt is reabsorbed into the blood, water goes as well, and so it's isoosmotic. But what it does do is it reduces urine volume and increases blood volume. This is regulated by something called the renin-angiotensin-aldosterone system, which we'll revisit again in chapter 17 when we cover renal physiology in more detail. But let's take a look at that at least a little bit here. So the way this works is that there are blood pressure sensors, a specialized structure in the kidney that's called the juxtaglomerular apparatus. And when blood flow and blood pressure is low, this causes the juxtaglomerular apparatus to secrete an enzyme called renin. What renin does is it converts a precursor molecule called angiotensinogen into another molecule called angiotensin 1. And then angiotensin 1 is converted as yet into another molecule called angiotensin 2 by an enzyme appropriately called angiotensin converting enzyme, often referred to as ACE. So this is the way this works. So as your blood pressure drops, blood flow to the kidney is lowered. The juxtaglomerular apparatus senses this, and it acts almost like a pressure sensor in a way. And this causes the release of renin. Renin then causes the conversion of angiotensinogen into angiotensin 1. Angiotensin 1 is converted by angiotensin converting enzyme. This is located in blood vessels to a very significant amount actually in the lungs. They're in other parts of the body as well, but a high concentration are in the blood vessels in the lungs. This converts angiotensin 1 into angiotensin 2. Angiotensin 2 then stimulates the adrenal cortex to cause the production and release of aldosterone. Aldosterone then causes the reabsorption of salt and water by the kidney back into the blood, and this increases blood volume. Angiotensin 2 causes vasoconstriction of arterioles, and we'll come back to that a little bit more, but that also then raises the blood pressure. So this just catches, then corrects, then the drop in blood pressure and drop in blood flow to the kidneys by increasing blood volume and increasing blood pressure. So let's take a look at aldosterone a little bit more. So angiotensin 2 has other effects in addition to causing the release of aldosterone. It, as I mentioned, is a very powerful vasoconstrictor. So small arteries and arterioles then constrict, and this helps to catch a drop in blood pressure that might happen with a drop in blood volume. It too has a direct effect. In addition to the osmoreceptors, it also has a direct effect on the hypothalamus in stimulating the sensation of feeling thirsty and motivates you to drink something. As I mentioned in the previous slides there, it causes the production and release of aldosterone by the adrenal cortex, which causes then the reabsorption of sodium, and water follows along with this, and this is going to increase blood volume and decrease urine volume. As I mentioned, angiotensin II is a very powerful vasoconstrictor, and so ACE inhibitors, the enzyme that produces angiotensin II, and the receptors that bind onto angiotensin II, antagonists of those receptors, are very common and frequently used treatments for hypertension. That is, they can then be used then to help to reduce people who are suffering from high blood pressure. So, as I mentioned, the heart acts as an endocrine gland by releasing atrial natriuretic peptide. And it is sensing then an increase in venous return and an increase, which would occur as a consequence of an increase in blood volume. And what atrial natriuretic peptide does is it promotes salt and water to be excreted into the kidneys, and then that then becomes urine, and so it reduces blood volume by increasing urine volume. It also inhibits antidiuretic hormone secretion, so it is going to reduce the number of aquaporins that are in the collecting duct, and so as a consequence, less water is going to leave the kidneys and be reabsorbed by the blood, and instead that water stays in the urine and helps to reduce blood volume. The book mentions it being a physiological antagonist of aldosterone. I mean, not really directly in that sense, but it works in an opposite sort of way. So aldosterone wants to bring salt and water back into the bloodstream, so reduce urine volume, increase blood volume. Atrial natriuretic peptide works the other way, and that is that it increases the secretion of salt and water by the kidneys, and the increase in increase in urine volume and a decrease in blood volume. So here's what this looks like again in a table. So something that would cause an increase in blood volume or an increase in venous return, your book mentions water immersion. Actually, if you immerse yourself in water, there's pressure put on your blood vessels that causes an increase in venous return. Hence, that's why that component is listed in this table here as well, this chart as well. But both of these will cause an increase in venous return. This causes a stretch of the left atrium. That is directly via the vagus nerve, is going to signal the brain, which is going to cause a decrease in the activity of the posterior pituitary's release of antidiuretic hormone. Aquaporins are going to be removed from the collecting duct in the kidney, and so more water is going to end up in the urine. You're going to increase in urine volume and a decrease in blood volume. This other pathway shows that the stretch of the left atrium causes the release of atrial natriuretic peptide. This is going to cause an increase in sodium and water excretion. That is an increase of excretion by the kidney in the urine. The urine volume will then go up. All of these together here are going to then reduce blood volume, and via this negative feedback loop then is going to bring blood volume and venous return back to normal.